Yeah, so just wanted to say thanks everyone for joining. It's it's early in the morning for a lot of people, so this shows some good level of commitment for learning about time series forecasting in Python, and that's no surprise because it's a very interesting topic. So first of all, who am I, and why am I talking about Python and forecasting? So I'm a senior data scientist in GSK Consumer Healthcare, and for the past year or so, I've been focusing exclusively on time series forecasting projects that we do in GSK. Along with Galina, we've worked on a project which is very similar to what we'll do today. And also, I've been working with the Sktime open source package, and I've been contributing there, which is also awesome. And we'll learn a lot about the Sktime package. This is going to be the main Python package that we'll use for our forecasting workflow. A few words about GSK Consumer Healthcare. We are the company responsible for any consumer healthcare goods of GSK. So Sensodyne, cold and flu, and our focus is to deliver better everyday health with humanity. Please join the live session if you can. We'll be there talking about, if I'm not mistaken, AI and complex systems in the supply chain, which is going to be a very interesting topic and something we're very, very, very interested in and working on. And now, yeah, let's jump straight into the aims. So we'll consider this workshop successful if by the end of it, you understand the time series forecasting problem, you know what tools exist to create time series forecasts in Python, you can manipulate time series data in Python, you can do exploratory data analysis, you understand the forecast evaluation metrics, their advantages and their limitations, you understand the importance of out-of-sample evaluation and cross-validation, you can implement statistical time series forecasts in Python, and you can implement ML forecasts in Python. The way we will run this workshop, I will be sharing my screen and jumping back and forth from slides, an ID where the classes and the code sits, notebooks, and we'll do some R stuff just to compare the Python workflow with our workflow. Although I'm a horrible R coder, so don't judge me. The context is going to be the introduction that we're going through now, time series exploratory data analysis, forecast evaluation and metrics, single time series forecast statistical methods versus ML methods. Then we'll do a small parenthesis on the M forecasting competitions because they've been a big influence in the forecasting world, and the results are always, they have a big impact into the trends of forecasting. And then we'll do panel forecasting and global forecasting methods, which means, forecasting many time series. At the end, I'll show you some additional resources, and then we'll focus on the Q&A. So whatever is left at the end of the session, or maybe if someone has a loaded question that we'll have to spend a long time going through. I've had a very humble beginning in the time series forecasting world, and this is me admitting my mathematical crimes. So my first time series project went like this. A long time ago, and when I was not working for GSK, I was asked to make 20K forecasts in a very short amount of time for a very long forecasting horizon. And yeah, there were a lot of problems with that brief, but the main problem was the fact that I didn't know what I'm doing when it comes to time series forecasting. I did a quick research on metrics, algorithms, asked a few friends, and I decided that, okay, with that amount of time, with the fact that I have many time series, the best metric to use is Mape, which is the mean absolute percentage error. And we'll see what the problems and what the benefits of Mape are. I'll do a single train test split. So keep the past, store some of the time series future, let's say, and then calculate my Mape on the test set. And then that's what I report. So I do this on all the time series. I use Prophet, which is a really good library developed by Facebook or Meta these days. I didn't tune it, of course, because I didn't know what I'm doing, and Mape was infinity. And Mape is infinity because if you have a single zero in your time series, because it's the mean absolute percentage error. So you divide your forecast error by the actual, then it's going to be infinite. So I realized that this is the problem. Also, stakeholders didn't care about the very granular levels of the time series. So let's say if we're forecasting, I don't know, products and categories and sales in stores, I was forecasting the products, they were interested in the categories. So I aggregated my time series. I made a hacky function for Mape to ignore cases where the actual is 0. And then I do it again. Let's say Mape was 20%, and everyone is happy. Then go to Databricks, scale those functions using, I think, yeah, it was a pandas UDF. UDF means user-defined function. And then the project is over. I have no idea about what the performance was in the real world, but everyone was happy. And of course, if you know anything about time series, you can notice a few mathematical crimes that have happened, in that story, and we'll go through them today in the session. And hopefully, by the end of the session, you will not do these mistakes. So let's talk about the time series forecasting problem. This is a picture from a very, very interesting paper on temporal fusion transformers for interpretable multi-horizon time series forecasting. But what I really like is how they frame the time series forecasting problem. And it really helped me clarify a few things and put some terminology in place to communicate with the team and also with stakeholders. So the way I see it, we have 3 categories for the data in a forecasting problem. We have the observed inputs. So these are the things where we only know their past. The known inputs, which are things that we know their past and their future. And this could be, what week of the year it is, for example. We know what that was in the past. We know what this is in the future. It can also be the price. So if GSK is doing a forecast of our own products, we control the price in many cases. And we know what the price is going to be in the future. And we can also have static covariates, and we'll see where those come into place. But these are features that don't change over time. So they're the same thing in time. And then we can also have point forecasts, which is going to be this line here. But in many cases, we're not interested in the point forecast. We're interested in distributional forecasts, where we can see also the prediction intervals. In this workshop, we will focus only on point forecasts. We can't cover everything in 3 hours, unfortunately. But I like to quote Georgi, who is a principal data scientist for supply chain, and he says, the probability of the point forecast happening is almost 0. So when you have to take decisions, when you have to aggregate forecasts and take decisions based on risk, the point forecast is not going to be that useful. The main forecasting textbook we'll use is Forecasting Principle and Practice from Rob Hidman and George Athanasopoulos. I've quoted this and then referenced it so many times in the notebooks and in the slides that I'll just refer to it as FPP. Forecasting Principle and Practice is a bit long. It's a great book. It's online, available from the authors themselves. So, I don't think it's an exaggeration if I say that I have a tab open of this book every day in my browser to just check something quick. Also, Rob Hidman is I guess the research and developer behind a lot of the forecasting packages in R. And a lot of good forecasting algorithms, and we'll see a lot more about this later. Here is the Python toolbox we will use for the workshop. We will use pandas, NumPy, interactive Jupyter notebooks, and Seaborn and Matplotlib for data processing and plots. So this is, I think, pretty standard. For forecasting, we'll use Sktime, stats models, and we'll also use PM Darima and tbats, which through their interface with Sktime. And for machine learning, we'll of course use scikit-learn and lightgbm. Now, what are the challenges of forecasting with Python? We have a classic R versus Python argument, and the reality of forecasting algorithms is that in most cases, algorithms are developed in R and then re-implemented in Python. And we can see many examples. So the forecast package in R is, I think it was introduced in 2008 by Rob Hidman, and it has a lot of good functionalities. And yeah, PMDARIMA is a re-implementation of the AutoARIMA function in R. AutoETS in Sktime is a re-implementation of the ETS function in the forecast package, and the same for tbats in Python. My eye caught like a very interesting conversation on LinkedIn with a few. I think it was started from a lecturer from Lancaster University. Lancaster is really good in forecasting. And yeah, I made a note of an answer. I asked the guy if I can quote it in the workshop. So someone asked, anything you find painful in Python when it comes to forecasting? And Philotas Theodosiou gave a really good answer. He said, easy, forecasting using statistical models. All libraries above are inconsistent when it comes to statistical models. For example, take ETS. On cats and darts, ETS is an extension of another library, stats models. I don't have the best experience with stat models, buggy and weird results. Plus, it is difficult to understand how to accurately fit a model due to bad documentation, which it's true, and I can relate to that. On the other hand, Gluon has ETS built on top of R, which is great. So why not use R in the first place? Yeah, and I think all these comments are valid. But why do we use Python anyway? And why do we have a workshop for Python? So I think for me personally, I prefer to code in Python, and I feel I have more freedom to do the things I want in Python. Also, I can leverage a lot of other libraries. And now that we can use machine learning for forecasting, I think Python can be a good choice. And of course, this is the choice I make, and this is why we're having this workshop. So now let me take you straight to the code part. Sorry, here we go. Of the session. So we'll start with exploratory day analysis. The data we're going to use are data from the Flu View dashboard from the CDC. And just let me make a view for the particular time series we'll use. And yeah, the CDC calculates, collects all the data about positive flu tests and other types of data. And then they make it publicly available through this dashboard. They also run a forecasting competition for flu called FluSite, although this competition was stopped due to coronavirus and the unpredictability in flu that coronavirus has brought. And what I did to find a data set to forecast for this workshop is I just downloaded the data from the dashboard. And I will add the data, the CSV with the data in the GitHub repo in case you want to reproduce the results. So I just want to bring the Q&A forward. Good. So exploratory data analysis is a crucial part in time series forecasting. This was the first mathematical crime I did in the example. And the fact that I didn't do a thorough exploratory data analysis. So let's see what we'll do here. So first we're going to read the data, do some classic info, describe, see the data types, and look at the very high level what we have in the data set. So we have 55 states for 12 years, and we have max 53 weeks per year. This has to do with the leap years. This has to do with the leap years and yeah, that kind of stuff. So we, in the data set, if you can see, we have the year and week, and we want to get the date to create a time series based on weekly dates. And to do that, we tend to use the ISO standards, because the standards, and you can create a new column that represents the date formats of the week based on the ISO standards. Someone says if I can zoom in, so I've zoomed in a bit. Is that all right? Can you confirm in the chat? Cool. Okay, thanks. So I've made a screenshot of a website that has the ISO weeks, just to see what years have 53 weeks, and sense check what I get. And then for some reason, the ISO calendar and what I didn't agree. Did a few other checks with the ISO calendar function in pandas, and then I realized that, okay, there's a problem here. And what I realized is that the CDC is using their own standard for week-year combinations that is called epidemiological weeks and MMWR. And to my surprise, there was a Python package for that, and there's also an R package, which is crazy. But this package takes a week, a year-week combination, and it turns it into an actual date, like this. So make a hacky function to do it on a pandas data frame, and suddenly, great, we have the weeks. I've named this column to DSWSun. Sometimes it's confusing when you work with dates and especially weeks. You don't know, okay, does this date refer to the Monday of the week and to the start of that week, or Sunday? And if it's Sunday, is it going to be the end of the week? So I like to name my columns very descriptively to keep reminding myself. The irony here is that end date here is Saturday and not Sunday, but we'll fix that later on using the period data type in pandas, which leaves no room for interpretation, because when you use the period data type, you don't have a single date. You have two dates, the start and the end of that period, and that's a really good functionality from pandas to remove all confusion. So we'll do some data validation. We'll check that we don't have any duplicated region week pairs. Those would be odd data points, and we'll see. We wouldn't know what to do with them. And we'll also check whether we have missing dates, and I've made a custom function to do that, which would give me, if we had any missing dates, it would give me a list of, a dictionary where the key would be the region, and then the value would be the set of missing weeks for that region. But likely we don't have any missing dates for any of the regions. We do have a lot of nulls, but those nulls are only in Florida and the Commonwealth of Northern Mariana Islands. And I think those, if I remember correctly, those are completely null, so we'll just get rid of them, and we will not forecast them. We also have a few zeros. We have 975 zeros. Sometimes you get 0 positive tests for ILI, and those are valid zeros. And the maximum week we have is 2021, October the 9th. And the reason we explicitly print how many zeros we have is, if you can recall the mathematical crimes, you can't really use Mape if you have zeros in your time series, and ignoring zeros is not good practice. You're interested into what your performance is, even if the actual values are 0. So that alone would rule Mape out from our metrics pool. So yeah, we'll do some filtering, filter out the null regions, limited to a start date. You know, we don't want to use all the dates available, and then we'll just start plotting stuff. I really like to use IPy widgets for this kind of plots and exploratory data analysis. So here we can see, okay, this is California, and this is the total ILI positive tests. ILI stands for influenza-like illness, and it's not necessarily flu because it's influenza-like illness. And the total is not weighted, it's just a sum. So we also get the weighted ILI. Weighted ILI is nulls in this dataset. We can get the percentage unweighted ILI. But for this workshop, we'll just use the ILI total. And this interactive plot gives us the ability to, you know, sense check all of our time series and just look at them. So we look at California, we can look at other time series. And although this is tedious sometimes, and especially if you have thousands of time series, it's good if you can just plot a few random time series and from your data set, look at them. If you observe that, okay, one time series has many zeros, plot that particular one, see what's happening there. You can see that there's a very strong pattern of seasonality in the time series, and that's classic because flu has a season. It peaks around, I think, January, and during the summer there's not much flu going around, and we can see that in this particular time series. Now, when we have many time series, a good thing to do is to check the correlations, see whether our time series are correlated, because that, you know, that would indicate that some methods will work better than others. So this is just the correlation metrics. Ignore that top part, it's symmetric, but we can see that, okay, in general, our time series are more or less positively correlated with each other. And now we dive deep into a single time series. We'll go deep into a single time series and do a more thorough exploratory data analysis in that time series. We'll choose California just because it looks nice. And the first thing we'll do is we'll create a few what people call seasonal plots. So this is the year of the week, and we have a different line for this is the week of the year, and here we have a different line for every year. And we can see, okay, this really shows that seasonal pattern we observed before, right? And more or less, we have a peak somewhere in January, then it goes down. At some point in August, it reaches its minimum, and then it starts going back up again. And this is like the flu season in a year. Another important plot we would like to see is the autocorrelation plot of that time series. And what autocorrelation means, and I'll have to do some hand signs for this, but imagine that you take your time series and then you just slide it like across different lags, and you want to see how correlated is your time series to the lagged time series of like 1, 2, and all the way to 54. And this also shows that seasonal pattern, okay? And the fact that the most recent values of the time series are also correlated. So we can see there's, I mean, zero lag is trivial. Of course, it will be 1, but then we have very high correlation on lags, like on the small numbers of the lags, then negative correlation when we come to the end of the flu season, or yeah, I mean 6 months apart, sorry. And then we also have a high correlation 52 weeks before. Now, the other thing we can do is decompose the time series. So we can assume that the time series is created by a few different components: the trend, the seasonality, and the errors or the residuals of that. And we can do time series decomposition. You can have multiplicative and additive seasonality, and this is a very nice interactive plot that shows this. So I just wanted to show you how it works. And that's a pretty nice test. You can do it. You can do it on your own time. So try to guess if this time series has an additive or multiplicative seasonality. So for me, because we can see the trend, but those seasonal peaks increase as the trend increases as well. So I will choose that this is a multiplicative seasonality, and I was right. This one, I will also go for multiplicative, but maybe I'm wrong. I don't know. Whew. Are they all multiplicative? Okay, we'll go for additive here. Wrong. And yeah, this is a fun test to test your intuition about what's multiplicative and what's additive. And you also compare your performance against various different statistical tests. So back to the decomposition. You can do decomposition with moving averages. And moving averages, you take the time series is a value per week, but we can create another time series that is going to be a sliding average of the past 3 weeks. And this is what a moving average is. And we can do a decomposition with that and break down the time series into seasonality, trend, and the residuals. And we can do that. You see the results here. We're using the stats model seasonal decompose method with an additive model. And yeah, I mean, that decomposition doesn't look great, but it is what it is. It picks up that seasonal pattern very well. And residuals are a bit crazy. So what's left after the decomposition is a bit crazy. We can also try our luck with a multiplicative model with moving averages. Or we can go a bit smarter than that and use the STL decomposition. STL stands for season trend decomposition with LOES, which is locally estimated scatter plot smoothing. And the benefit of STL compared to moving average is that it allows for changes in the seasonality. So if you see here, the seasonality is the same throughout time, but STL allows some changes in the seasonal patterns of the time series. So this is the result. The problem with STL decomposition is that if you just use STL, you can't have multiplicative seasonality. But there's a workaround to that we'll see soon. What we do after the decomposition typically is to analyze the residuals. So if we plot a histogram, ideally we want the residuals to be to have a mean on 0. Normally distributed helps with a bunch of things as always. So we always plot the distribution of the residuals. And we can also plot the autocorrelation of the residuals. And if an STL decomposition would do a great job of decomposing the time series, then that autocorrelation plot wouldn't be like that. It would be a bit like random. So we wouldn't see any patterns here. The fact that the autocorrelation plot looks like that, and we can also observe, that okay, we do have some weird patterns there that that they don't look like white noise. Means that okay, STL is not enough. We need to use like a forecasting method to effectively forecast this time series. You can also do a log transformation to jump from additive to multiplicative seasonality using STL. So if we do STL on on the logarithm of the time series, and then we transform that again back. We go from additive to multiplicative seasonality. And again here, we have maybe it's a bit smoother, but yeah, we again have like weird residual patterns. And that brings us to the end of the EDA notebook. I'll take a pause to see if we have any questions specific to exploratory data analysis, and then I'll move to my favorite part of this workshop, which is around evaluation and metrics. Okay, good. So it looks like we don't have any unanswered questions. Thanks, Galina, for answering everything. And now we'll move to the forecasting metrics and evaluation part of the workshop.
Yo, we have one question. I just flagged them that it will be answered live. So the question is, when doing exploratory data analysis, what kind of insight do you want to get?
Yeah, great. So we want to see if we can identify a few things for our group of time series, right? So how correlated they are is one example. If a good example is if our time series is full of zeros and very interrupted, and that can happen with sales and stuff like that. Howard, just to answer your question, the majority of the high level things that we're talking about does come from that book. Like, it's an excellent book. If you read it end to end, you'll be in a very good place, let's say. The only problem with that book is that it's the code there is in R. And so let's say answer live on this one. And Deborah, we will share the GitHub repo, and you can work on this at your own time. The data is going to be there, and everything is going to be there. So it will be very, easy to reproduce everything and make changes and hopefully improvements. But yeah, we don't want you to code along, just because a few of the algorithms are going to take some time. So I've run these notebooks in advance, in order to have a smooth presentation. But yeah, we'll share everything, and you'll have like the code base and everything to play around. And back to Galina's question, a good example is intermittent time series. If we have intermittent time series, we're very limited, not limited necessarily, but it pushes us to other things, using other methods, using other metrics, and stuff like that. And if the majority of our time series is, for example, intermittent, so we have, let's say we have weekly time series, and we have 10, 10, 0, 0, 5, and then 0, 0, 5, and we have a lot of zeros. Then we need to do other things, use other methods, which I will have links into the presentation. Yeah, so now let's talk about forecasting metrics and time series cross-validation. So one amazing thing about Sktime is that they have an extension template, and you can create your own models that you can use with the rest of the Sktime library, because we can't just make a model any way we want, and not respect the Sktime API and then think that it will work. So in my case, just for this notebook, I wanted to create a forecasting algorithm that that gives a constant value that we add in the options, and that's it. And you see later why, but I just wanted to show you that extension template from Sktime and how you can use it. And here we go. So, and you can find this in the documentation of Sktime or in their GitHub. And how it works is you can copy paste the extension template, rename the class. I've named it constant value forecaster, Of course, I didn't write a doc string yet. I was trying to get things done fast. It has all the tags that Sktime needs, that operate on the backend. So like ignores exogenous X. And the exogenous variables can be, the observed and known inputs, for example. Requires forecasting horizon and fit. All that is there for us. There's a template for the init function. So in my case, init takes a value called constant, which is the constant value that the forecaster will yield. And I just assign it to the constant. And then the underscore fit method, the predict method, and then here we don't fit anything, so we just return self. It's fine. And then in the predict method, whatever we predict is going to be just that constant. So really simple stuff. But if you want to create your own model that and you have an algorithm, maybe you've seen it in a paper, you want to implement it, but you want to use all the awesome stuff from Sktime, like the metrics, cross-validation, grid search for tuning and stuff like that. It's a great idea to just use that template. So back to that notebook. So we'll use a few things from Sktime. We'll use a naive forecaster. They have some utils for plotting, which are great. They have various cross-validation strategies, classes, and also functions for error metrics. And yeah, I've also made some helper functions to process the raw data, get the single time series, and stuff like that. So to demonstrate effectively a few things around the metrics, we'll create a synthetic time series, but we'll also use the California time series from before. I've just created, 10 plus a log normal distribution. And what this time series is, it's just noise, right? There's no pattern. So it comes from a log normal distribution. So it's not normal, which has some properties like that, in a normal distribution, the mean is equal to the median, but in a log normal, it's not. And we'll see why these properties are interesting for some of the metrics, etc. And of course, California. So even if you're the best forecaster in the world, there's no harm in trying a naive approach first. We have a few different naive methods. You can use a simple moving average, and we call it simple because moving average is another thing. But a simple moving average is, let's say we want our forecast to be the average of the last 5 time steps. So did I pick 5 here? I picked 10. So that simple moving average is, I guess maybe I have to zoom in again. So yeah, that simple moving average is the average of, like, let's say those data points. And you can also have the naive method, which is my forecast is going to be the value for the latest value of the time series. And that works well for non-seasonal data. But if you have seasonal data, maybe you want to use that seasonality. And we have what is called seasonal naive. And seasonal naive is, let's say we have yearly seasonality. We'll say, I want to take the equivalent value from that time series for last year. Okay, if you don't have a year's worth of data, that's your problem, but you wouldn't even notice that seasonality. So, you won't have that problem. But if you have, many years worth of data, you can use seasonal naive. And those naive methods are now our first forecast that we'll use, but they become the benchmarks for the start of every forecasting project. Our first goal is to beat the naive methods. To evaluate performance on those first examples, we'll use the mean absolute percentage error, or Mape, as I call it, and many people call it Mape. And here's the formula for Mape. It's 1 over the horizon for the absolute error divided by the actual for the forecast. Mape is a very, very common forecasting metric due to its interpretability and scale-free properties. But by scale-free, I mean, it's something of one scale divided by the same thing of that scale, so it's unitless. And what this means is that if we have 2 time series, it's not a mathematical crime to take the mean of the Mape. Some people will argue that it's not the best thing to do, but at least it's not a mathematical crime. We'll compare it with other forecasting metrics in the next section. But for now, let's start with Mape. So what we'll do is we'll create a temporal train test split. And then that will give us the test data to calculate Mape on for our naive forecasts. It's important when you create train test splits to take time into account. We're working with time series, and we want to predict the future. So just randomly taking points like we do, for normal regression, is not going to be any helpful. And here are the results. If we take the simple moving average, if we take the naive, and if we take plot it against the test set. So Harun asked, are there any rules of thumb for the length of time series data that the models perform well? That's a very interesting question. So I've had the luck of working with some old school forecasters, and they do have rules of thumb. Like they say, okay, for ARIMA, you need blah, blah, blah data points. For ETS, and we'll see those algorithms later, you need blah, blah, blah data points. Otherwise, don't even bother. I don't have that experience. As I said, I've been focusing on forecasting for a year, and I don't have that, those empirical rules. But I'm sure if you go to cross-validated, you will see many people with opinions about those rules of thumb. My best suggestion is use cross-validation to see what the best performing algorithms are. If you don't know those rules of thumb and you don't trust them, use cross-validation, which will, again, sorry, I'm introducing things that I haven't talked about, but we'll see it like it's the next section. So use that, see what the performance algorithms are. And the way I see it is, if you're a very experienced forecaster and you know those rules of thumb, you trust them, it will just limit the time you need to get to the best model, because you will not waste your time with models that are not going to work. So I'll just say that this is answered live. Yeah, good. Mape is a bit disappointing here. We have a Mape of 300% and 200%, which is pretty bad. And then we can see the same thing for the seasonal time series of California, highlight total. Here you can see that for a long horizon, seasonal naive gives us a pretty decent Mape. And what you will notice is that there's a pretty big gap here with the test set and the very low naive method, but we have only 50% Mape. And in this case, the gap is not that crazy, but we have a huge Mape. And this has to do with a few problems with Mape that I will illustrate down the line. So time series cross-validation. A single train test split, will give us the performance of that test split, but maybe we got lucky, maybe we were unlucky. To increase our confidence in our estimates for Mape and any metric we use, we need to do a time series cross-validation. So take the time series, say, okay, this is the past and this is the hypothetical future, the test set, and we'll slide that window across as shown here. These are the images from scikit-learn. We'll slide that window to have many trained test splits, like in cross validation, like in K-fold that you would use for regression or classification to get an estimation of the performance of our algorithm that will be more confident with. You can do this with many ways. You can have an expanding window splitter. That means that an expanding window splitter is this. So you start with a small train set and this, the same value, the same length of the test set, and then you will slide. So you will increase the train set size and keep the test set fixed, and you will go like this. Here's how this looks like in a cross-validation setting. So here we're taking seasonal naive. We'll do an expanding window splitter, as it's called in Sktime. We'll start with an initial window of 4 years, and we'll slide this for 20 weeks at a time. Sorry, that's still an expanding window splitter, but instead of sliding it, no, this is exactly what is shown in this graph. So yeah, we'll slide it for 20 times, and we'll calculate the test set on the horizon. So you can see we start from here, and this is our seasonal naive prediction. This is the actuals. Then we go to the next slide. So there's no overlap between those two windows, but we can also create situations where there is overlap, to get more trained test splits out of the data we have, and we calculate the seasonal naive Mape across those cross-validation splits. And you can see, okay, again, we got 22%, which is okay, good or bad, it is what it is. We might also want to test specific points in the past. And this is the cross-validation method that we'll use for this workshop. We do this because imagine you have seasonal data and you want to have an accurate view of performance, but you don't want to test like many different splits by doing a sliding window, for like, I don't know how many times. You can do 100 different sliding windows if you want. So in this case, sometimes we might want to say, okay, I'm interested in the performance here, which is the peak, but I'm also interested in the performance here, and I want to see different situations, and on those dates and see how my model performs. And this is how this looks like. We can pick the August of 2017 and the December of 2018, and this is how this would look like. Okay, so starting from August, this is how it goes. Starting from December, this is how it goes. And then we can take the mean Mape across those splits. I'll take another pause, see if we have any questions on the cross validation, but it looks like we don't. And I like it, yeah. So someone said something from Lancaster and Nikos Kouretses. I'm not sure if I mentioned that, but this is the Nikos Kouretses blog. So yeah, I am a fan of what comes out of the Lancaster University and Nikos Kouretses. And then we have another question. Thank you for your workshop so far. Say that the beginning of COVID, you don't have enough data points. How can you build the model to ensure your forecast is accurate? That's a really tough question. Yeah, so you can, if you have a very short time series and you're interested in a long forecast, that will put you in a situation where you don't have the data to do cross-validation on the length of the time series that on the length of the horizon that you want. So let's say I have 1 year's worth of data and someone wants a 2 years forecast or a 2-year forecast from me, I don't even have the data to test what my performance is going to be over a 2-year forecast. And yeah, of course, that's a problem. My first suggestion is to go to and say, why are you interested in a 2-year forecast? It's, you know, we can do it, of course we can do it, but we'll have no understanding of performance for that forecast. We don't know, we don't know what, you know, what the performance is going to be, and I'm not confident in saying that, okay, this forecast is X accurate or has a Mape of this or that. And I would even challenge why someone needs a 2-year forecast with 1 year's worth of data. And then the other thing is, sometimes I say, okay, a human expert in this case would give you a better forecast than statistics. So if you want a 2 years worth of forecast with 1 year worth of data, maybe just go to a human expert. Like, let's say someone wants to see how COVID will develop in the next 3 years at the beginning of COVID. Okay, we haven't observed anything. We don't know if it's going to stop, if it's going to, if it, in 2 years, 1 year, 3 years, if it's going to have a big impact. At that point, you know, we will trust human experts, and there's the field of judgmental forecasting, which is, you know, human experts giving their opinion, I guess, of the future, is a big field, and it's actually studied by forecasting researchers quite a lot. But if you have a short time series and you're interested in doing a forecast, and what you're worried about is, okay, how do I select the best model? There is an answer for that, and we'll see it later on in the next, I guess, notebook that we'll go through. So I'll say answer live. I hope that answers your question, but if it doesn't, you can ask again, and we'll give it more time later. So forecasting metrics. As I said in the beginning, we will focus on point forecasts only. So we have scale-dependent error metrics like RMSE and mean absolute, root mean squared error and mean absolute error. And we also have percentage error metrics, which which are not scale-dependent, like Mape, but also symmetric Mape, which is this weird formula down here. The problem with RMSE is that we can't take the mean across many time series, because let's say we have a time series that's in the scale of 100 and the time series that's in the scale of 10. And RMSE is going to be dependent on that scale. So the RMSE of the big time series is going to be higher just because of the scale. And then if we take the mean, we would almost care more about performance on the high scale time series than the small scale time series. And in most cases, this is not the right thing to do. We care about performance on all of our time series. So now what we'll do is we'll calculate forecasts for the synthetic data from the log normal distribution. And we'll see what the performance is on of different forecasting algorithms, I guess, on that synthetic time series. For the forecasters, we will take the mean of we generate the distribution, we know what the mean is, so no surprises there. We'll take the mean, the median, and just a small number, which is going to be 50 in this case. And then we'll use the RMSE, the mean absolute error, Mape, and symmetric Mape, also called Mape, to evaluate the performance with respect to all these metrics. So I'm not going to go into the details of this code because I just checked the hour. It's 10, so but it will be there in GitHub for you to see. Evaluate is a function from Sktime that you can give it as cross-validation strategy, and it will, you know, generate a report based on the scores and everything, which is really good. And then I've also made this hacky like function here that highlights the mean value of in a table across rows or columns. So let's see the results. The results are really interesting here. So if we just say, if we just say the forecast is 50, which is that orange line here, that minimizes the Mape. With like, you know, we can see that the Mape is 60% if we just say the value is 50, and that beats all the other algorithms, so the mean and the median. And remember, this is just noise, so there's no pattern. We just want to see if we only had noise, what value would we have to estimate of that of the time series to minimize its error metric. So if we take a small value, that will optimize Mape. If we take the median, that will optimize mean absolute error and symmetric mean absolute percentage error, or SMAPE. And if we take the mean, that will optimize the root mean squared error. Yeah. Now, here is the histogram of the synthetic data. And based on what you've seen above, you can, I think you can now understand what the problem is with Mape, right? It really penalizes when you over forecast compared to when you under forecast. And this is why people created the symmetric Mape. But the symmetric Mape is it's a tough metric to understand, and you know, and explain to the stakeholders. So we now have some derivation on why this happens. You know, there's a mathematical reason why root mean squared error is going to be minimized from the mean, and mean absolute error is going to be minimized for the median. And we just do like, okay, we want to minimize something with respect to x, because if you think about it, the task above is can be, you know, the exercise, let's say, is what is the constant value that minimizes its metric for that particular time series. And we can do this, okay, we, you know, in a very hacky, you know, back of the envelope maths, if you can consider you know, derivatives as back of the envelope. So we'll say, okay, let's take the derivative of mean squared error, which is going to be equivalent as minimizing the root mean squared error with respect to x, which is that constant value, and set it to 0. So, you know, if the derivative is 0, this value will be minimized. And if we do the math, we end up with x equals, and then the definition of the mean. If we do the same thing for the mean absolute error, we end up with the fact that x needs to satisfy this this relationship here, which means that this needs to be equal number of times 1 and minus 1. So x needs to be equal number of times greater than y and smaller than y, which is, of course, a condition that is satisfied by the median. The median splits the data in half. I would love to have done the math for Mape and symmetric Mape, but I didn't. Apologies. And I have a few links here that you can check later. So this is explained in the standard textbook, Forecasting Principles and Practice. And there's a lot of good discussion on those threads in Cross-Validated. Stefan Kolasa is a well-known member of the forecasting community, and he was very active in Cross-Validated. So I think, yeah, most times, most of the times where I want to, like, where I end up here, and, you know, for a forecasting question, usually the answer is from Stefan Kolasa. So yeah, I think the guy deserves a lot of credit because he gives very thorough answers into this kind of forums. Of course, we've talked about the problems with RMSE and that they're scale dependent. This is overcome by the percentage error metrics, using scaling them with actual. But then we have another pool of problems, and the metrics that people have engineered to overcome all those problems are the scaled error metrics, and the root mean squared scaled error and the mean absolute scaled error are given by those formulas. And if you just look at this, you're probably thinking, what the hell is this? How am I meant to understand it, and let alone explain it to one of my project stakeholders? And I'm really proud of making this graph. I've used it, in projects and in the past to explain what the root mean squared scaled error is. So it's just, if you take the normal root mean squared error that you would use for your forecast, that's the top part, and the bottom part is the root mean squared error of a one-step naive forecast in your in-sample data. So in-sample is the train set, out of sample is the test set, and again, the RMSE is the error that a naive forecasting algorithm would have in your train set. And we just use it to scale the time series and take advantage of the scale-free properties of those error metrics, where we can take the mean of those errors across many time series, and we can compare apples for apples. You can also have the seasonal variance of those metrics. So in this case, if you think that your time series is really seasonal, you can say, I will use a seasonal naive forecaster to scale this, and this is the formula to do this. And of course, if we look at what's happening, the mean will optimize RMSE and RMSE, and the median will optimize Mape and Mace, I don't know, because we're just taking that value and scaling it by something that is more or less constant. For the next sections, we'll use the root mean squared scaled error as the main KPI, because we have many time series. We want to compare them in a fair way, but we have zeros. We don't want to use Mape, and we also don't want to under forecast severely. So again, we don't want to use Mape. And now let's go into actual forecasting. And in this notebook, we'll focus on forecasting a single time series. So it will be California again, and we'll create the rules of our forecasting experiment, and those rules will not change for any algorithms. We want to evaluate our forecast in 8 different cutoff points, in the off season, in the start of the season, in the peak, and in the end. Ideally, if we were more thorough, we would just use a sliding window, but that would mean we would have too many train test splits, and running this from a laptop for the number of algorithms I've run is just a bit too much, and I was getting annoyed with the amount of time it was taking. One of the reasons is the code here is not parallelized, because of some issues I've had with like OpenMP, but I'm not going to go into the details. But in the cloud, of course, the code will be parallelized, and you would be able to do that a bit faster. But yeah, here are the Oh, and of course, we'll use RMSE as the metric we will evaluate all forecasts at. So here is the custom cutoffs plotted across time. So here's 1, 2, 3, 4, all the way to 8. And as always, we will do a naive benchmark. We'll do a seasonal naive and a naive. I think I forgot to mention, but we'll evaluate things on a 3-week ahead horizon. So we'll just forecast 3 weeks ahead, a short-term forecast. And the naive performance is better in this case just because of the short time horizon that we have compared to the seasonal naive. And yeah, here is why. So you can see this is how the seasonal naive does. In the off season, it's like perfect. And here is, sorry, this is the naive, and here is the seasonal naive. Okay, we've seen the naive methods before. Now it's time to get real. And I think I'll go through this section, and then we can take a small break, grab a coffee and stuff like that. But let me give you something to think about during your coffee break. So my favorite statistical method is exponential smoothing. The fact that it's my favorite means nothing, of course. But there's a bunch of reasons to like exponential smoothing. So exponential smoothing is probably the oldest forecasting method. It was proposed in the late 50s, and yeah, it was introduced by Brown, Holt, and Winters, and sometimes you will hear about exponential smoothing as the Holt-Winters method, for example, or the Holt method, and stuff like that. It has motivated some of the most successful forecasting methods, and we will see later, what those are. And effectively, a forecast produced from exponential smoothing is a weighted average of past observations, with the weights decaying exponentially as the observations get older. So if you compare it to a simple moving average, in a simple moving average, we say, take the mean of the past 10 observations and just take the simple arithmetic mean of that. But in exponential smoothing, you penalize, I guess, the contributions to that value of older observations compared to newer observations. And intuitively, that's a really smart thing to do. And yeah, I think this is from the Forecasting Principles and Practice Introductions. This framework generates reliable forecasts quickly and for a wide range of time series. The simplest form of exponential smoothing is called simple exponential smoothing, and it's defined as, the formulas here. It has 2 parameters you have to tune, alpha and lambda 0. Sorry, L0, the level. And we do this by minimizing the SMAR of squared errors in the in-sample set with a non-linear optimization algorithm. So it's not like, you can't do it without optimization like you would do linear regression, with OLS. You have to use an optimization algorithm. Those were considered, so simple exponential smoothing, the Holt method, the Holt-Winter method were considered, I guess, and empirical methods. They didn't have a statistical framework behind them, which meant, a bunch of bad stuff. So you couldn't calculate confidence intervals. You had no concept of likelihood about them. But lately, now it's in the early 2000s, we had a new approach to exponential smoothing, the innovation state space approach, and that provided a statistical framework and a few other models using multiplicative errors, multiplicative trends, and multiplicative seasonality. And under this framework, exponential smoothing is as successful as it was, but it also has that statistical foundation, and you can generate prediction intervals and everything. And under the state space approach, there are 36 possible models. You don't have to memorize those equations; they're all in the book. And yeah, it makes exponential smoothing a family of models that's very powerful. How do you select the best exponential smoothing model out of those 36 models? Now, that's a big question. And I really like this topic. I've even asked like a question and cross-validated and got a few answers, but not the answers I was looking for. You can do model selection. The simplest way to do it is to do cross-validation. And as we compared seasonal naive and naive approaches in the past, in the earlier sections, compare all those 36 models and their performance in the, their mean performance in the cross-validation splits. This is probably the most foolproof method, but that takes time, and there are other methods to do model selection. And back to the question about, okay, what do we do if we have short time series and we can't do, really good cross-validation? Then you can use information criteria, which are things that are basically calculated in the in-sample set. So in the train set, you don't need the test set for information criteria. And you can use information criteria to select the best model out of the family of exponential smoothing models. The most commonly, but the only information criteria I've seen used for this is the archaic information criterion, the corrected archaic information criterion, and the Bayesian information criterion. So AIC, AICC, and BIC. And for the above information criteria, you can think of them as something that tries to maximize the likelihood that of the various forecasters, with a penalty for the number of fitted parameters used for the model. So if you can remember simple exponential smoothing, you just have to fit 2 parameters. But the more complicated the model becomes, the more parameters you'll have to fit. And what the intuition behind the information criteria is, because we're calculating it on the in-sample set, if we use a more complicated model, we will get better in-sample performance. We can even use polynomial regression and completely overfit the thing if we want. So we need to penalize. Our criterion for selecting the best model for the number of parameters it's using. And for some examples for some models, I think just the additive models of the exponential smoothing family, the likelihood is, basically equivalent to the sum of squared errors. So you can think of it as minimizing the sum of squared errors, but with a penalty for the number of parameters. And a good example is, okay, if simple exponential smoothing has the same number of the same sum of squared errors as exponential smoothing with additive trend and additive seasonality, then the model with the smallest information criteria is going to be simple exponential smoothing, because it achieves the same in-sample error with less parameters. And yeah, I think one thing to note is that, and I think there might be some debate on this topic, but I'm not an expert to give my opinion. So if something is debatable, I like to take the most conservative approach. But you can't use information criteria to compare models from different families. So we'll see ARIMA later on. You can use information criteria for ARIMA, but you can't use information criteria from ARIMA to compare them with information criteria from exponential smoothing. The automatic algorithm that selects the best exponential smoothing model from using information criteria, which has some other smart stuff because some models are unstable, and things like that. But it is not just that, but it's very close. comes from that 2008 paper, Automatic Time Series Forecasting, the Forecast Package by R, from Rob Hidman, who is also the author of Forecasting Principles and Practice. And it's, it's built in the famous Forecast R package. And as we've seen in the slides, the majority of the Python implementations are mimicking the Forecast package in R. Yeah, a good video to watch if you're interested in forecasting is the Uncertain Futures, What Can We Forecast and When Should We Give Up, from Rob Hidman. He did that like earlier this year. And he explains how they developed automatic exponential smoothing to forecast, I think it was forecast the spend of the Australian government for different pharmaceutical drugs, because they were supporting the population with funding some of that, and initially they were just way out of budget because of a bad forecast. They brought Hindman in, and he explains how they saved millions of dollars using this algorithm. And there is a whole book on forecasting with exponential smoothing and the state space approach. It's on my to-do list to read it. I haven't. The math there is crazy for some of the models. So if you're really interested, I suggest you read it. And of course, there's a high-level introduction of all those concepts in forecasting principles and practice. So at this point, let's take a coffee break. Just a quick refresh. There's this great algorithm called, it's called ETS in the forecast package, but I call it automatic ETS, so automatic exponential smoothing. And the automatic part is about the model selection and which model we'll choose. We have three information criteria that we can choose as the thing we're trying to minimize. And as I said before, I don't have much intuition about what's best, although I'll share some thoughts. So I like to try everything. So we will create, and this is the implementation from Sktime. We will try the automatic exponential smoothing, and we'll try it with AICC, BIC, and AIC, and we'll see what works best. And in this case, we see that AIC and ICC have equivalent RMSSC, but BIC is much better. There is some intuition to why, and I think that was my question to some degree on cross-validated. So if you have a forecast that you're interested in that has a big step or a big horizon, like let's say 12 steps, there are some theoretical there's some work that says that AIC will optimize for the one-step horizon, so it's equivalent to a cross-validation under some assumptions. Of course, it's equivalent to a cross-validation for a forecast with one-step horizon, but probably seasonal naive is pretty good for one-step forecast. What do we do if our forecast is a much longer horizon? And that guy said, I think there may be something about AIC optimizing one step ahead, but BIC optimizing several steps ahead and stuff like that. But I didn't go to the bottom of that mystery. I know that we have some really strong people from the forecasting community in the workshop. So if anyone has links to a paper or something, paste them in the chat. I'll look at them later as well. But yeah, that's a small parenthesis. You can see that auto ETS with BIC works best, and here are the plots. They are better than the naive case, and that workshop wouldn't be fair if we don't mention ARIMA, which is the other very popular family of models for forecasting. ARIMA stands for Autoregressive Integrated Moving Average. and integrated stands for like the for differencing the time series, which is something you do to make a time series stationary. So you say, you know, you slide the time series in lag, and then you subtract it from its original self, and that's differencing. And you can do different levels of differencing. I won't go to all of the details, but this is the point of the workshop where I was tired of typing forecasting principles in practice. So FPPP chapter 9 is all about ARIMA. You sometimes will hear SARIMA, that's seasonal ARIMA, and yeah, it's seasonal because it works with seasonal data. ARIMA is not you know, equipped without this. Normal ARIMA is not equipped to work with seasonal data. And then we also have TBATS, which is short for trigonometric seasonality, box Cox transformations, ARMA errors, trends, and seasonal. This Medium article is from the author of the TBATS library in Python. So if you're interested in TBATS, I suggest you start from there. Trigonometric seasonality is something that comes up a lot. It has to do with creating features from a Fourier series to capture complicated seasonalities. Like, you know, imagine if we have a time series that has a daily time series, and there's seasonality in the week. So Monday to Sunday, we observe some seasonality there. There's also seasonality in the months, from the beginning of the month to the end of the month, and there's also seasonality in the year. We can create different features for those different seasonalities using Fourier series, and then use those features to do our forecasts. Yeah, we'll see later, you know, why this is good. But yeah, normal exponential smoothing models will not do great with very long seasonal periods or complex seasonality. Also, Profit from Facebook, which I mentioned in the beginning, is very popular because it has an automatic way of generating those Fourier features, and it's really good with very complex seasonalities, just because of that feature. ETS and ARIMA models do share some, you know, basically some ETS models are equivalent to some ARIMA models, but they're not just, you know, they're not equivalent model families. So, but it's good to know that in some cases, if you do a MA1 model, it's equivalent to a simple exponential smoothing model. So, you know, maybe not try both. So this is where we'll go into a bit detail with you know, and do more complicated things with Sktime. A big motivation to use Sktime is the forecasting pipelines. So let me explain to you a few things to you know, motivate why we want to use forecasting pipelines. But effectively, we're having weekly data, and you know, the authors of FPPP suggest that if you have weekly data and long seasonal periods, which in our case is 52, exponential smoothing and seasonal ARIMA will not do great. And they suggest, I said 2 here, but they suggest 3 approaches. One is to use Fourier features that we explained before as exogenous variables. And exogenous are additional predictors other than the time series. Do an STL transformation and then fit an ARMA model, so not an ARIMA model, an ARMA model, because we've done the transformation, so we don't expect any trend, or a simple exponential smoothing model on the residuals, or use TBATS. And yeah, and it's very common to combine forecasts with box, Cox, or log transformations to stabilize the variance of the time series. And there's a very nice interactive plot here that I wanted to show you. I think it's here. Yeah, good. So this is the pure time series. This is how it looks. And then if we slide this to 0, then this is equivalent to taking the logarithm of the time series, and you can see that the variance, right, has stabilized. So we don't see increasing variance with time. And again, here is the original time series. So you can see that the variance is increasing as the trend is increasing. And then, you know, if we use the Cox transformation, we can eliminate that, and that makes forecasting much easier. So this is very common. You don't have to manually pick lambda. There's an algorithm that's called the Gerero Algorithm. It's very old. I think it's before 2000, maybe even in the 80s, that optimizes the lambda for a particular time series to stabilize that variance. And here's how the Cox transformation works. It's the logarithm of the time series if lambda equals 0, and then it's basically you know, lambda to the power of y, the time series to the power of lambda, minus 1 divided by lambda, and then multiplied by the sine of y. You know, you do this because you don't want to raise a negative number to its, you know, to a square root accidentally. So this is y. And going back, so we use the forecasting pipelines from Sktime to experiment with all of those things. And I've just made, you know, a few helper functions to try various different forecasters and just get, you know, a nice report at the end. So let's go through the forecasters one by one. So the first one is season trend, STL and SES. So what the author suggests as one thing to try for long seasonal periods. The next one is a log transform. So, you know, the equivalent of doing a multiplicative seasonality STL. And then SES. Then Cox, STL and SES. Then taking the log and going for an auto ATS. And in the end, T-bats. Oh, sorry, that's not the end. And T-bats, you know, which is the other suggestion, and then the final suggestion, which is do Cox, then do STL, and then use an ARMA model. We'll try all of those into our time series, and then we see that the best algorithm by far is T-bats. So it almost justifies that argument about, okay, if you have complex seasonality, use T-bats or do these other things. And let's see. So log and SES performs really well as well. STL and SES doesn't perform as well. Log and auto ATS is also good. But yeah, not as good as ETS with PIC as we've seen here. And remember, we're evaluating everything on the same splits. So it's a very fair comparison. And here we can see the forecasts. One thing that I forgot to mention is that SES is called SES because it produces like a flat forecast. I mean, yeah, not just because of that, but be mindful that SES will just produce a straight line as a forecast. So if we go here, you can see the example somewhere. Yeah, here. So you have a weird time series, and then your forecast is just a flat line. Another common practice that was, you know, also we saw a lot of evidence in the M competitions about its value is combining many different forecasts. And you know, you can be smart about optimizing the weights of, you know, of what its forecast will contribute to the final forecast, but taking simply the average will work well. And to some cases, it works better than anything else. You know, in the textbook we're using, They go as far as claiming as the results have been virtually unanimous. Combining multiple forecasts leads to increased forecast accuracy. In many cases, one can make dramatic performance improvements by simply averaging the forecasts. And there is also a channel in YouTube from the Lancaster Center of Forecasting that, they upload a lot of webinars on forecasting. And one webinar was with Nikos Kouretses, who is he's one of the leading researchers in hierarchical forecasting, and I think I've used a lot of his work for intermittent forecasting as well. And he has a beautiful explanation as to why taking the simple average works better, and providing some theoretical motivation. So I'll share the link in the slides for the Lancaster YouTube channel, and you can go there and find that video as well. So I've named that, again, luckily enough, we have Sktime. It gives us the ability to create an ensemble forecaster. So we take this class, and then we just stick in everything in. So log STLNSS, auto ETS, T-bats, this, that, the other. And we observe that at the end, the sum, okay, it doesn't beat T-bats in this case, but if you think about it, the average is much better than. So when we sum when we use the ensemble forecaster for those forecasts, the performance is much better as if we just averaged the errors from here. Which is, it shows that forecast combinations, using combinations of forecasters as your final forecast has a lot of value, and you can find a lot of examples as to why, especially from the M4 and M5 compositions. I do realize I've been talking about M competitions a lot. So now that we start talking about machine learning methods for forecasting, I think I need to give you an introduction to the M competitions and M5 in particular, which is what inspired the methods we'll see in the final section of the workshop. And also give credit to the organizers, the winners, and stuff like that. So let me do the intro now to motivate you about using machine learning in forecasting. So in the most recent years, machine learning methods have been climbing up the ranks in forecasting performance. The first sign of ML's potential for forecasting was in the M4 competition, where the winning algorithm was a combination of exponential smoothing and recurrent neural networks. The approach is explained here. It was an engineer from Uber who won, and they've given like a really good blog. They've made a really good blog here about their solution. However, the majority of ML approaches didn't beat the statistical ones in M4. The M5 competition was a different story. Almost all of the top level submissions used the combination of lightgbm models. I think there was an LSTM there, and lightgbm is a gradient boosted tree algorithm from Microsoft, and it has some really good stuff. More importantly, it's super fast. So you can do super fast means a lot of things. When it comes to competition and stuff like that, you have more time to do hyperparameter tuning. You have the luxury of doing more thorough cross-validation, because you can fit more splits in the time. So now let's go back to the slides for a deep dive into the M competitions and M5 in particular. So who is M? It's not the head of MI6 in James Bond. M is Spiros Makridakis. He's a very well-respected forecasting researcher, and he's the organizer of the Makridakis or M competitions. now he's, I think, yeah, he's in the University of Nicosia, and there's a website. There's a website where they share a lot of things about them, competitions, forecasting. They have a course that you can take on forecasting for practitioners, I think it's called, and yeah, a lot of resources there in the site. I think I have a link in the slides. The M competitions started in 1982. So the original M competitions had 1,000 time series, tested 15 methods, and we went into 87 to 93, 29 time series with 16 methods used. The M3, I think M3 was also like a big competition. It's still widely used as a benchmark data set for forecasting. It had 1,000 time series of multiple frequencies, yearly, quarterly, monthly, and other. And then, yeah, and they've used 15 methods. M4 that we talked about, 100,000 time series. It was open to a wider audience as a competition, and the winner was that guy from Uber with the hybrid ML exponential smoothing approach. And now let's go to M5. So some quick facts about M5. The M5 competition started in March 2020. It differed from the previous 4 competitions in 6 important ways. So first of all, it used hierarchical sales data from Walmart, which means that the time series in the competition are not independent. Okay, there might be a relationship like in our time series where we're using the same, the total ILI observations in different states. There, the time series were the sales for different store product combinations in Walmart in the US. Besides the time series data, it also included exploratory variables such as price, promotion, day of the week, special events like the Super Bowl, Valentine's Day, Orthodox Easter, normal Easter, that affect sales, which are used to improve forecasting accuracy. It was a double competition. It wasn't just about point forecast. There were 2 competitions: point forecast accuracy, but also distributional forecast, so uncertainty. And they're referred to as the uncertainty of the accuracy competitions. The majority of the 42,000 time series displayed intermittency, so sporadic sales and many zeros. And what's the other one? And instead of a single competition to estimate both point forecast and the uncertainty distribution, there are 2 parallel tasks using the same dataset. Okay, I spoke about that. The competition was hosted on Kaggle, and the total prize was 100,000 K. And I think the prize giving ceremony and the M5 conference is happening this December in New York. Some details about the data, I'll just skip through that. But here is the hierarchical structure of the dataset. So you have the total, right? That's one time series, and then you have the state, and then the store in the state, and then then we go to the hierarchy. So that's one hierarchy. That's the store hierarchy, and then we have the other hierarchy. This is the category, the department, and then finally the items. So yeah, a very rich hierarchy that people really took advantage of. The metric was the weighted root mean squared scaled error. We know about the root mean squared scale error. They weighted it with the sum of the sales in value for the last 28 days for each series. So the argument there was, we don't care about a product that is not generating value and profit as much as a product that is generating value. We want to a forecast that is more accurate for the high value generating products. Yeah, and here is why they've used the root mean squared error, but I will skip this. I think we've seen the motivation for that metric. What I really found interesting was the benchmarks that the organizers created. So the organizers created the benchmarks in R, And if you go to this GitHub link, you will be able to see the actual code for those benchmarks. And we're talking about, you know, the top researchers in the field of forecasting. So there's a lot of value in taking those out. They had ARIMA variants, exponential smoothing variants, special methods for intermittent time series, which is crossed on TSB, IMAPA, hierarchical methods. We're not going into the detail for hierarchical methods, but just briefly, top down is when you take, for example, the category forecast and you split it in the department forecast. And bottom up is when to forecast the category, you do 1, 2, 3 forecasts, and then you sum them up to get that forecast. Ooh, spoiler alert there. But yeah, they also implemented their own machine learning methods and global machine learning methods, which is something we'll get into later. And the best benchmark they chose was bottom-up exponential smoothing models. So again, out of all these things, exponential smoothing was what the organizers chose as the benchmark they will compare solutions with. The results, just lightgbms everywhere. There was, I'm not going to click on this link, but this is the original post. You can go into it later about, you know, I think about using lightgbm. And we'll go through the forecasting strategies. I think a key fact here is that the winning solution used a simple average, as we said before, like simply just combining and taking the average of multiple lightgbm models across different levels and recursive, non-recursive strategies. We'll see what this means later. Using the Tweedy loss instead of like a more conventional loss function like root mean squared error. And the reason was because of the intermittent functions. You can see how a Tweedy distribution looks. It's a distribution that has a lot of zeros here, and then it looks like a log normal otherwise, or something like that. The winners against the benchmark, I think the winning solutions were, of course, better than the benchmark. But let me see my notes. I think there were some interesting results. So less than 50% of the competitors outperformed the naive benchmark. 35% of the competitors outperformed the seasonal naive benchmark, and only 7.5% of the competitors managed to beat the exponential smoothing bottom-up benchmark, which was the one that the organizers chose. And that's no surprise. We have the best researchers, you know, creating the benchmarks. As normal humans need to put a lot of effort to beat that. The key findings from M5. The key findings were that the superiority of simple machine learning algorithms, you know, lightgbm is simple compared to crazy neural network architectures. The value of combining, the value of cross-learning. Cross-learning is when you train a single model on many time series, and the model is learning from multiple time series instead of like a simple univariate approach. The significant differences between the winning methods and the benchmarks, the value of effective cross-validation strategies, and the importance of exogenous and exploratory variables. M6 is coming soon. It's going to be about financial forecasting, and I think it's the top 50 stocks from the S&P 500 and some other ETFs and stuff like that. If you're feeling lucky, go there. I think the prize money is really good, and so yeah, I think it's going to start in February. So now let's go back to the notebooks and see what's up with the ML methods. Oh, and sorry, I'm jumping around a bit, but to show you the equivalent workflow in R, I've made like you know, a short R script using a package developed by Hidman, but it's not the forecast package. It's called Fable, and it's more convenient when you have many time series. And let me just show you that before we go further. So, you know, we just using those libraries from R. Again, I'm not great at R. The majority of this code is just copy pasted from the forecasting principles and practice book and just adjusted so that it works with my data. And yeah, we'll create a table object. So it's called a time series table, I think, or whatever. We'll do the same filtering as we did for in Python. We'll create a cross-validation strategy, a bit different in Python. I couldn't find you know, an out-of-the-box method to do custom cutoffs, so I just did a sliding window. But I made sure that we have 8 splits, and then, you know, and this is how we just do the forecast, right? We put the CV, the cross-validation splits in as the data. Then we use that pipe thing in R. We define the models we want to use. So here, naive, seasonal naive, and exponential smoothing. And we say, okay, take these models, forecast for. Noor, sorry. The name of the package is called Fable, but it belongs into a universe of other things. I'll just paste all the libraries in the chat. The MMWR week is something for the epidemiological weeks. I think that we said in the beginning, so no need to use that. And if you go through the 3rd edition of forecasting principles and practice, you will see code with Fable everywhere. And then the other package is called Forecast. And if you go to the 2nd edition of forecasting principles and practice, all the examples are with the Forecast package. And the difference between Fable and Forecast is that Forecast is developed to do forecast for a single time series, but Fable is developed to just, you know, really quickly with that amount of code produce as many forecasts as you like with all the methods available in Fable for a group of time series. You do this with a table object by make the code bigger. How do I do this? Anyone in the chat knows how to zoom in RStudio? Oh, that didn't work. And this is why I don't use R. Anyway, just bear with me. We won't stay in our world for a long time. Here's what we need to do to make the forecasts. We can then get a beautiful accuracy report just with this function. And then I also have this code because this is something I use at work sometimes. If someone wants an ad hoc forecast really fast, I use this package, generate the forecast, and then create a PDF with all the plots and just give it to them. Here is the accuracy summary, exponential smoothing infinite Mape because we have some zeros, and then mean RMSE for ETS and naive and seasonal naive. These are not comparable to the other numbers we see in Python just because the cross-validation strategy is not the same. But yeah, it's super easy to create good forecast fast in R. Back to Python, and the R code will be in the GitHub repo. Yeah, so it's going to be here. Actually, I'll just paste a link of the GitHub repo in the chat as well. Back to the notebooks. So to use machine learning methods for forecasting, I guess the most popular way, I'm not aware of many other different ways to do it, but you need to somehow reduce your forecasting problem to a regression problem. I would like, I think, you know, that I've picked up this terminology from Sktime. I'm not sure if someone else said it first, but this is the image from Sktime to, you know, that explains how the reduction process, how the reduction works. So your forecasting problem would be like this. So from 0 to 9, forecast 10, from 1 to 10, forecast 11, etc. So this is a time series, and this is going to be the test set, and then you tabularize that. You create, from a time series, you create a table now that has the values of the window you want in the columns. So let's say we want to create a table with the 10 past values as the features we will use, and then we want to predict, you know, the next time step. We will take that time series. I'm not sure if I printed here anyway. I don't, but it's all right. Show you later. We will take that time series with the dates, and then we'll transform it into a table where we'll have lag 1 as one column, lag 2 as another column, lag 3, and then those will be our features, and then the dependent variable will be y, the target, what we want to predict, and then we will just, that way we can train any regression algorithm that we want. There are 4 main approaches for ML-powered multi-step forecasting. Because a single time step, you can just do this. That's fine. But if you want to do many steps ahead, you can't just do this for and have a single target variable. So Noor, I'll get to your question later. So Noora is asking, is the tabular data you mentioned key value pairs, tidy data, if you will? I'm not very familiar with the tidyverse, and we'll see later, like the implementations for the multiple time series that we'll use here are custom implementations from me, but they mimic that key value concept you're saying, using the pandas indexes, and yeah, I'm not sure what's the best approaches for Python, and you know, this is an active discussion with the developers of Sktime to see what the best and the most you know, appropriate way to do this is. Sorry, quick time check. I'll need to get a bit faster. So again, the 4 approaches for multi-step forecasting. Multi-output. So let's say train a neural network, and then you have a vector output. Its element in the vector corresponds to the time step. Direct is direct is another method that we will use here. It is going to be, we train a model per time step, and because the tree-based, like, boosting algorithms don't have multi-output, you have to do that anyway. So multi-output, if we're using lightgbm, for example, is out of the question. And then we have recursive models, which some people call autoregressive, which is going to be, we train a model, a single model that will predict the next time step. And to predict more time steps, when we'll make the first prediction, then we'll take that prediction, stick it in the appropriate lag column, so in the inference set, and then predict the next value, and then we'll keep doing that. And this is how the recursive approach works. And the recursive approach is very powerful, but it comes with some issues into you know, training, calculating prediction intervals, but I think those are tackled in the research. And then you can have the mixed approach of a direct and a recursive algorithm, where you train a model per time step, but you also include those recursive features. This is the first article I saw from Machine Learning Mastery about those different strategies. So I've put a link. It says the same thing, but in a better way. So Sktime has all of those features already built in, and we can also do transformations using pipelines. So I've just put everything in the kitchen sink, sorry, like all the different combinations of things I can imagine to see what will be best. And you know, as a data scientist, I want ML to beat the statistical methods. So you know, I was a bit biased to put a lot of effort in the machine learning approach. So let's see what's happening. And yeah, you know, I've tried all the combinations. The pure lightgbm recursive strategy algorithm is the one that beats all the other machine learning algorithms, but it doesn't beat any of the statistical approaches, which is sad. And here, remember, we're working on a single time series. We're using the make reduction function, class, function or class, I can't remember, from Sktime, and we're using a lightgbm regressor to power the predictions. But results, compared to the statistical approaches, results are disappointing for that time series. But at this point, we don't give up. We have an ace in our sleeve when it comes to the machine learning methods. And this is going to be global forecasting algorithms. So zooming in a bit. Leonidas has an interesting question. He says, do you believe combining all models, building an ensemble, would outperform these scores? Yeah, to be honest, it's a bad idea. I didn't try it. But in general, yeah, combining models tends to do better. So if I had to guess, I would say yes. We did try a combination of statistical approaches here. So it's this case. It doesn't beat the bats, but it does pretty well. And then I guess what Leonidas is saying is, what if you just add all those models from that, you know, using the machine learning approach? Would it do better? And most likely it would do better. And Leonidas is the guy I quoted about what the pains are for forecasting in Python in the beginning. So thanks for joining, Leonidas. It's a pleasure. So yeah, let's go to the final chapter, if you want, of this workshop, where we will do what I call panel forecasting. So we will not forecast just a single time series now. We will forecast all of our 50 states. Here is the here is the data frame that we will use: region, value, dates. Same cutoff periods as before. And you know, now we will go to my own weird custom implementation of those algorithms. So we will divert a bit from the beautiful Sktime API, but these functionalities will be part of Sktime in the future for sure. So the first approach is to do one forecasting algorithm, a univariate forecasting algorithm per region, right? We want to predict many time series. Well, you know, the simplest thing we can do is just train a single forecasting algorithm for every time series and then see what's up, see the results. To do that, I've created my own class that's called Sktime Panel Forecaster, and let me show you what it does and how it works. Sorry, it's not that one. It takes any Sktime forecasting algorithm, and then we have to specify what the name of the column is, that is the time series ID, and what the target column is, and what the frequency of the data is, and stuff like that. But then we just, you know, for each time series, right, we fit a different forecasting algorithm. We store the model in a dictionary. So the dictionary will be time series ID as the key, fitted model as the value, and then when it comes time to predict, we loop through that dictionary to get the prediction for the time series. Simple as that. So no real science here. It's just a wrapper function to give us the power to use Sktime for forecasting algorithms without writing for loops every time, like here. This is an example using the naive approach. The mean root mean squared error across all series is 1.2. And something I forgot to mention is that if you remember, if you go back to the definition of what root mean squared scaled error is, it doesn't mean that if it's greater than 1, your algorithm is worse than the naive algorithm, because the denominator, which is the naive forecast, is calculated on a one-step forecast every time. Doesn't matter what our actual forecast is, the step, the horizon. So in this case, our horizon is 3 steps. So if we see that the root mean squared scaled error is greater than 1, doesn't mean that, you know, we should give up and just use naive. And this is what you see here, right? The naive forecaster is having a root mean squared scaled error of 1.23, just because we're testing a bigger horizon on the top part of that fraction. I've made also this helper function to choose different time series, because now we have all the time series. We want to see what's the performance for all those time series. So, you know, that's handy. And then the best performing algorithm from California, when we did the single time series tests, was the T-Bats algorithm, you know, and with good motivation about why. So using the Sktime panel forecaster wrapper class, we'll create, we'll train a T-Bats for all the time series, and this will be our benchmark. You can see that the root mean squared scaled error across all series and all cutoffs is 1.16, much better than the naive approaches. For California, it's the same as it was before, and then, you know, we can check. Let's check Nebraska, or, you know, Mississippi and stuff like that. Okay, so really good performance overall, and because we're using a scaled error, we can take the mean approach of those errors. And now let's go down to the global forecasting algorithms, which is, you know, what won in the M5 case. So by global forecasting algorithms, what we mean is we will use a single model. So in this case, a single lightgbm model for all of the time series. If you think about it, this is great from a computational power perspective, and time. So training a single model or a single lightgbm model is way faster than training many T-Batch models. So again, that gives us a lot of time to tune, do more cross-validation splits, and stuff like that. This is a custom class, the direct lightgbm global forecaster, and I'll show you the code. It's also in the GitHub. And to capture the seasonality, the yearly seasonality, I've also made some dummy calendar features, like the week and stuff like that. I've also had year and trend, but when I did some experiments, they were throwing the predictions off, so I just kept the week here. And of course, we have categorical features now. The region is a categorical feature, so we need to treat it in a way. We want to encode it, maybe do label encoding. lightgbm is good because it treats categorical variables differently, so we can do some smart stuff there. We can do target encoding, which is what I think, where you take the category, you take the mean, for example, the mean that region has in the historical values for the time series, and you encode it that way. So, you know, this is machine learning. We can engineer our own features, and we're very flexible there in that regard. And I think I've also added a log transform by default, because empirically adding a log transformation gives you better results in some cases. Let's look at the code. So this is the global forecaster. This is the direct approach. So, and yeah, this is a very hacky implementation of this. Sorry, I saw a question. Well, we'll get to it later because we're about to finish that section. Yeah, so we'll use a label encoder to do the categorical variables, specifying those things, what the ID column is. We'll do a log transform, the lag window length, as in the reduction case from Sktime, so it would be 12. And these are just the settings for lightgbm, but for the workshop, we're not doing any tuning or any grid sets. We will create the calendar features. So just simple, the year, the week, and T is just time. So 0 is the first point in the time series, and then all the way to the length of the time series. We'll create the multi-step targets, and also the lagged features, and this will create basically a new data frame. The multi-step targets are going to be called ILI total _ H1, H2, H3, and the lagged features are going to be called ILI total lag1, lag2, all the way to the length of that window that we chose. And then we'll also process the categorical variables the way we want them to. In the fit case, we'll initialize the lightgbm regressors for each time step, because this is the direct approach. And then we'll just do a for loop. We'll do that feature engineering within the fit case. And this is important because when you do tuning and grid sets and stuff like that, you want to play with everything in one go. And this is why that feature engineering happens there. You take a hit in time, but it's a trade-off you have to think about. And from experience, I've done both, and I prefer if I do that kind of feature engineering within the fit. It also ensures that you don't accidentally create leakage problems, and we'll see what leakage means at the end of the session. For every time step in the horizon, we'll just train the model, and then when it comes to predicting, we'll just do the same for loop again. Sorry, I'm not going into crazy detail in the code because we're running out of time. And when we use the the global methods, we significantly outperform T-Batch. And you can see that California before, with the machine learning methods, was only doing 1.2 24 RMSSE, and in the global case, using the same algorithm, no tuning, it does way better, and that's impressive. That's the value of cross-learning that we saw in M5, and also the mean is significantly smaller than the case of TBATs. We can also do the recursive approach of a global algorithm. So I'll just skip that and go back to it in a second. And here is the recursive approach of the global lightgbm forecasting algorithm. Here is the score for California. It's even better than TBATs in this case, but the mean is not as good as the direct approach. And then again, no tuning, nothing. The benefit of this, it's a bit faster because you're just training one model, but we can see that the mean of the RMS is smaller in the direct approach. A good thing to do is analyze the residuals. We're just taking a mean across cutoffs, time series, and stuff like that. We want to see if there's some funnies there, and there are. An RMSSE greater than 20. That's 1. And then we have another one that's greater than 10. And if this was a project, then we would deep dive into those particular time series and see what the hell is happening there, why we get such high errors. And then the other beautiful thing about using lightgbm or any tree-based algorithm is we can look at the feature importance. And here I've just retrained it and plotted the feature importance for every algorithm in the direct approach. In the recursive approach, it would be equivalent to this one because it's the same algorithm, right? It's a one-step ahead algorithm. So you can see that the weak feature is very important. The latest value of the ILI is very important. The lag one, the region value, and then all the different lags. And that's another very important thing to tune, right? Maybe doing only lag 2 would give us really good results. Maybe we need to do 52 weeks worth of lag. That will give us better results. That's something we can play with. We can also play with different transformations within the global time series, as we can do a box Cox for every time series, as long as we remember to inverse transform later. I didn't add this functionality in this class, but it's a good idea to do that. And then, it's interesting how the feature importance changes for different steps. Here, it's very similar, but the region is more important than the lag, the lag value, and here the region is even more important. The further away we go into the horizon. And then, the same residual plots for the recursive. So I think this is all the code I wanted to show you. It's feel free to clone this. The data is there, and experiment with different things. Try to tune the lightgbm algorithms, tune do different feature engineering, compare them with more statistical approaches. I think depends on what your definition of fun is, but for me this is really fun. And now let's go back to the presentation for some closing remarks, and then we'll dedicate the remaining time for Q&A. So, remarks. These are my personal opinions, but hopefully, having watched this presentation, you can relate to a lot of those things. Carve the time to do a thorough exploratory data analysis on your time series, and don't commit to deadlines and accuracy targets before you do. Nathan is the principal data scientist for marketing in our team, and he has this quote that I really like to quote. It's EDAs before ETAs. So we don't give you an ETA about the project before we see the data. And the second point is pay a lot of attention in framing the forecasting problem. Do you want a point forecast or a distributional forecast? Do you want a cross-validation? How your cross-validation will be? Are you going to use custom cutoffs, what is the metric you want to use? And then, do you want to forecast weekly or daily? Do you want to, is there a hierarchy? Do you want to use hierarchical methods? All these things should be part of when you're scoping the problem and you're trying to construct what, what I like to say, your forecasting problem. Third point, always test the simple benchmarks like naive, seasonal naive, and exponential smoothing. Don't go straight to LSTMs and RNNs. It will be embarrassing if someone comes in later in the project and they test the seasonal naive and it beats your method. So always bear that in mind. Test the naive approaches. They're really good benchmarks for what comes next. Don't disregard judgmental forecasting methods. They have their place, and we can't always beat them. And this goes back to that point. Okay, if we have if we have short time series, we want a ridiculous forecast horizon. What do? Go ask an epidemiologist, a public health expert in the case of COVID when it first started. Statistics is not, and ML is not the answer to all of the problems. And we need to be pragmatic about that. So if in your business people use judgmental forecasting, don't disregard this as a primitive approach. Take it seriously. Intermittent time series. They are special. Treat them with care. Google cross them to start. I'll leave it to that. And don't use Mape for intermittent time series. If there's a hierarchical structure in your time series, it will probably help you in making better forecasts. And that relates to the second point. Consider combining forecasts to get better results. If the absolute best forecast you can do is a bad one, there is still a lot of value in quantifying that uncertainty. And we've seen this in GSK with things that are very disrupted with COVID. Stakeholders take value from the fact that we can tell them, we do cross-validation on our forecasts. Our performance is really bad at this time. We're trying to improve it, but just bear in mind that we're going into uncharted territory. The other point is be mindful of leakage in your forecasting experiments. Especially when we start engineering our own features, we can create a forecasting experiment or frame the forecasting problem in a way where we leak the future into the past. And this is a big problem because it means when you release your model into the wild, into production, then you will see a big discrepancy between your cross-validation results and your actual results when you monitor performance in reality. And leakage is defined as when we accidentally leak information that we don't have at the time of the forecast in our cross-validation and offline evaluation. Other point, again, linked to this, continuously monitor forecast performance. If you introduce leakage and you monitor performance, you will catch it, you will fix it. If you don't, you'll just, give city forecasts to your stakeholders and no one will know about it. And our final point, you've probably understood that I like the ML methods, I prefer the ML methods, but let's be pragmatic. If my global, deep, blah, 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 autoregressive model is only giving a small uplift in performance compared to exponential smoothing, I will go for exponential smoothing. It will be way easier to maintain in production. I will not have to worry about things I would worry with a very complicated model. So be pragmatic about what that performance uplift is with using more powerful models, and in many cases exponential smoothing will be the best choice. And finally, some resources on time series forecasting. I'll just voice over them. That video from Rob Hidman is absolutely great. Uncertain futures and what we forecast and when should we give up. Any video on the YouTube channel from the Center of Marketing Analytics and Forecasting is really good, very insightful. Yeah, I mean, I would suggest having a look at the video from Courageous on hierarchical forecasting. That was really good, but everything there is brilliant. And then there's this link from Sktime on the Sktime presentation, PyData. I think they had another presentation as well recently, but I didn't find it on YouTube. Some blogs and websites. Hindsight is Hindman's blog, the Courageous blog that we've looked at both of the interactive plots. At one of the interactive plots, and then the International Institute of Forecasters. They have a podcast. They have a journal. They do seminars, and it's a really good community to keep an eye on and pick up the latest things in forecasting. Books. I'm not gonna say FPPP again. Okay, you got the drill. It's a great book to get started with. Forecasting with Exponential Smoothing, the state space approach. There's a new book on intermittent demand forecasting, which is very handy if you're struggling with intermittent demand time series in your projects, and it also gives a lot of other good things around stock optimization, inventory and stock optimization and stuff like that. It's a really good book. Time series analysis by state space methods. This was, I think, when I was panicking around that first project, and I asked a friend, do you know any good books that I can go through? He said this one. I didn't end up reading it, but in the end, but it's it's a textbook I go back to sometimes to see a few things, and then I'm conscious that I said, clone this thing from GitHub, play with it, blah blah blah. If you don't know anything about GitHub Bash, etc., and Git, try that the MIT Missing Semester course. It's really good, and it will speed up your development when it comes to those to using Git, the Bash, etc. And then, yeah, I think that's it. So let's finish up with a famous quote from baseball coach and player Yogi Berra. It's tough to make predictions, especially about the future. Which reminded me. And then we'll go into the Q&A. If at any point in your life you have to deal with someone using in-sample Mape, so not Mape from a test set, or even worse, 1 minus in-sample Mape, use those two arguments. So for 1 minus in-sample Mape, this is commonly referred to as accuracy. Mape can be more than 100%. So if someone is using that, or if you're using 1 minus Mape, in any case, you might end up in a position where you would have to say we have minus 100% accuracy. And I wouldn't want to be in that position. Also for in-sample Mape, or in anything in sampling that's not an information criterion that penalizes for overfitting, the easiest way to optimize for that is just to overfit. So it's tempting to do stuff like that, especially when you don't have good grounding into the forecasting theory and stuff like that. But the easiest way to convince someone that this is a bad idea, take your algorithm, let's say you're using a lightgbm model, tune the parameters to overfit the hell out of it, and then report the training Mape and the validation Mape. Your training Mape, because you've tuned the parameters to overfit, will be very small, and your validation Mape will be huge. And then ask, what do you care about? But yeah, now I'll just have a look at the questions and start answering them one by one. So let's start with the simple stuff. How do we get the links? Is the presentation available? We'll make the presentation available and we'll email it. As I think, I'll have to check with our comms department, but we'll definitely email it. Worst case, we'll just email the resources and the links. You mentioned not to disregard judgmental forecasting. How can you incorporate it into time series forecasting model? Thanks. That's a really good question. Nothing is preventing you from adding the judgmental stuff as features in your machine learning model. Or an ARIMA model with exogenous variables. So you can do that if you want. You can also test your performance against the judgmental forecast. If you have the historical judgmental forecasts and people store that, you can do that too. So your creativity and is the limit here. You can do anything with that. And then the other question we have is, I could not get the idea of futures creation for the ML models. If we use the time series lags as features, when we do predictions, how can we create the new sample? For instance, say we created the features from the time series data from November, and we would like to predict November 2021. How can we create the features of the new sample to feed the model? That's a good question. Maybe if we have time, I can show you how it's done by using the protected methods in the classes. But effectively, when we do the fitting, I then create something that's called the pred-df, and this is what I will use later for the inferencing. So if you see here, I will take the latest value of my training data. I will drop the targets. I will drop the target variables, and this is the target variables here will be null, 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 null. So we'll get that. That's not useful for training anyway. And when I do the prediction, so this is self underscore pred-df, you can see where it's used, right? So take that the model that corresponds to that time step and predict based on that table here. So I hope that answers your question. Otherwise, we can go into a bit more detail if we have time at the end. So I'll mark it as answered, but if you have more questions, just type another question and we'll go there. Matthew Weller, any particular version of Sktime to use with your repo? Didn't I put it in the requirements? Let me check. I'm using the latest version, but just checking. Okay, yeah, sorry, I'll hard code some of the versions here and make a new just make a new commit. I'm using the latest version of Sktime. It had some fixes and some features that I really liked. So yeah.
Yeah, I think all the versions of all the libraries are printed in the first notebook.
Yeah, but not Sktime, I think. So pandas and stuff is there, but not Sktime. To be honest, yeah, the majority of the other libraries are coming from Sktime. So I will just specify that, use the, I think it's 0.81, the version of Sktime. So I'm using that one. What else? Leonidas, great talk. Do you have any recommendations, advice for using Bayesian models to create upper, lower credibility intervals using PyMC3, PyPro, or similar? Yeah, that's super interesting. So Prophet is a Bayesian model using Stan. I haven't like created the custom implementation of Bayesian methods. So I don't have any recommendations, but I think there's a great blog about someone who recreated Prophet with Pyro. So if I find it, or if you Google like recreating Prophet with PyMC3 or Pyro, Oliver, you will find it for sure. And it's just, it's absolutely brilliant to get you started and get me started, because I want to do it as well. Can you tell us more about your team at GSK and what type of data forecasting you're working on? Is most of your work project based on other teams? Do you also maintain software in production? Great question, Dimitri. We do maintain products in production. This workshop is inspired by something that's already in production. It works on many different countries, and it's a lighter version of that product. As a team, I see ourselves as an enabler team. So we go and we fix problems and we create products that help key functions of the business. So we have dedicated principles for marketing, supply chain and finance, R&D, and finally, to answer your question, we have the machine learning, dedicated principle for machine learning engineering, who is responsible for taking us from code here to code in production. If you have more questions, we will be in the live data science festival where Georgi and Emma will give a talk about AI in complex systems and the supply chain. I'm butchering the title, but something along those lines. And I'll be there as well. You can also reach out to me on LinkedIn if you have any questions or you want to chat. I'm really happy to chat about forecasting. That's how I met Philotas, because Philotas he has the final question, but Philotas published a brilliant paper using deep learning methods for temporal aggregations, and I won't go into more detail because I'll butcher it, but it's a brilliant methodology inspired by an algorithm called Thief, so temporal hierarchies and something else, forecasting. And I saw that. I reached out to Philotas to chat about forecasting, and we've been chatting there ever since. So Philotas' question is, thanks, Leo, for the great talk. Quick debate question: what is your opinion on deep learning models, and how do you measure performance threshold when you go for a simpler model? For the last part of the question, I would say that depends on the use case. It's a bit empirical, and it's a conversation with the stakeholders. We can develop an exponential smoothing model faster than a deep learning model. So maybe a nice process is develop a simple model first, see whether it meets your requirements. If it does, you can stop there. If it doesn't, go deep. Try to do deep learning models, global forecasting models, all that jazz. And then the question you need to ask yourself is, does my effort in the future to maintain this model justify the performance uplift? And there's no rules of thumb on this. It depends on the use case and then the stakeholders and you. Finally, when it comes to deep learning models and maybe as opposed to lightgbm models, one of the issues is with deep learning models, there are some architectures that you can use, but again, tuning it and all of that stuff, it's a bit more demanding than lightgbm. Of course, you need to tune a lightgbm model, and we achieved that performance with the global forecasting algorithms without even tuning it, which is very impressive. But if we do like proper hyperparameter tuning, we'll do much better. I think the first global model I've shared of was in Amazon. They've used the deep autoregressive model, so using a recursive strategy with a deep neural network. And also there's a good talk again on the Lancaster forecasting channel. The title is very misleading. It's called How Machine Learning Methods Are Not Changing the Supply Chain, but it's misleading because it then goes into describing how you can frame your forecasting problem again to make the most of neural networks and stuff like that. So yeah, I think neural networks are promising, but they come with their own problems in terms of tuning and stuff like that. Beautiful. And I think let's see if we have any other questions. Alex Rapidis. So do you have enough time in a typical day-to-day project to test simple methods, SES or ARIMA, versus more complex Sktime RNNs? Do you have a go-to solution that you usually turn into? Yeah, great question. I mean, a project is, is a long time. You have typically a long time, and simple methods take less time to develop. There's some wrappers in this code base that I use to do quick comparisons and generate forecasts really fast. I didn't have those in the beginning. I started developing them. Now you have them too. Great. You can even make them better. And Sktime also gives you, a really good functionality to do things fast. But I would never, I think I've learned that lesson, that I would never do, a global lightgbm model before testing exponential smoothing, and I would never do exponential smoothing before doing a naive benchmark. So I think having that mindset of gradually increasing the complexity of your models is a good rule to have. But of course, different projects have different needs. And Harun has a question: can you suggest references to the ML feature creation, etc., and deep learning on time series? Let's go to Sktime in this case. So Sktime has some auto feature generating, automatic feature generating things. TS-Fresh from Blue Yonder, I think, is a good one. I haven't used it personally. I just create simple lagged features and go from there. Another thing you can do is create summary statistics using a lagged, like a rolling window. So instead of just the lagged features, create the equivalent of that lagged feature, but in a rolling mean, a rolling standard deviation, a rolling, I don't know, kurtosis. You can pick as many moments as you want. And that will probably give you better results. But yeah, what I want to show you is, I think it's here, it's series as features. What was it?
Leo, I don't think you're screen sharing, just if that matters.
Oh, did they stop?
Yeah.
When did they stop?
I'm not sure, but only for this last little bit. But I don't know if you want to screen share just so people can see that bit.
That's a surprise. Yeah, sorry, I was in the Sktime GitHub repository, and I was trying to find. There's this thing called TS-Fresh that generates features from time series. Catch22 is another, and these are all motivated from research and stuff like that. And yes, I am using the latest release from Sktime. Another remark is that Sktime was the first open source contribution I made, and one of the reasons is it's a very friendly community of core developers. They were very patient with my mistakes in my first pull request, and they really mentored me to get that done, which was for me a big goal and the big achievement. If you want to play around and if you want to play around with Sktime, you can. Where are the docs? API reference. Here we go. Go to the documentation, and you can find, where are we? In the development section, you can find the developer guide. Let's see. So getting started guide, developer guide is here. In there, you will find anything you need to go from not knowing anything on how to make an open source contribution to be able to make a pull request. So I think, yeah, it's that section, how to contribute. And they have very detailed instructions on how to do so. So if you're interested and you want to give it a try, I suggest you start from there. And this is what I did, and it worked. And all of the good packages have equivalent guides. You just have to find them. I am sharing now, right?
Yes, yeah.
Good. I think, yeah, we don't have any other questions. So I guess one final remark. If you're in the live session, come visit us. You know, we will be there, and don't miss the talk, because it will be great. You know, Georgi and Emma have some really good insights on the topic of complex systems and the supply chain. So it will be epic. And don't quote me on that, but I think, you know, we have a few positions available in the team. So you know, check them out. Come to talk to us. Reach out to me on LinkedIn if you're interested. And that's it. Thank you very much.
Amazing, Leo. Thank you guys so much. I'm going to actually ask Galina to turn on her camera and mic as well, because she's been, yeah, incredible. So yeah, massive thank you to you both. That was 3 incredible hours. I think we had about 50 questions over the chat and the Q&A, and they were all answers. Thank you so much. Leo, if you want to go into the chat, you can see everyone. Nor, you know, fantastic. Thanks to Leo and Galina. Bruno, nice. Haroon, thank you, Leo. Organizers, a great presentation, great workshop. Thank you for taking the time to share your learnings on a Saturday. There's loads. Matthew, utterly brilliant session. Leo, thanks very much for giving your time on Saturday. Fantastic talk. So there's loads and loads as you scroll up, just saying thank you. What a great session, full of explanations, theory, and practical tips, as well as a clear process, examples, and human learning resource. So loads and loads of thank yous in the chat. And again, if you haven't thanked these guys, please put something in the chat. It's really hard to see if anyone's there, so it's great to see all the feedback. So yes, thank you both. Galina, thank you so much for helping with the Q&A and answering all those questions. Absolutely brilliant. And Leo, amazing 3 hours. Yeah, massive thank you to everyone at GSK Consumer Healthcare as well for putting this session together, and also you guys for running it today. Yeah, if anyone wants to come, obviously the ballot is being drawn for the November 27th live event. You can just go to datasciencefestival.com and click live and apply for a ballot ticket. It's free to come along on November 27th. Make sure you check out, obviously, GSK's presentation on that day, and we will get the recording of this up probably on Monday. So if anyone has any questions, feel free to ping me on Slack, and I'll do my best to get everything up. But how was it for both Leo and Galina? How are you guys doing after 3 hours?
I mean, time flies. I really enjoyed all the questions. Thank you so much for the lovely comments. And Galina, thanks for answering all those questions. You almost left like zero work for me. So yeah, you know.
You're welcome. But
so
there were not so many questions, and yeah, I tried to answer all of them promptly. Yeah, so 3 hours just flew away.
Yeah, it always goes super, super, super quickly.
And yeah, sorry, Jess, thank you so much for hosting. And you know, of course, I'll watch all the other seminars as well. Yeah, good luck with the rest of the Data Science Festival, and hopefully see you on the live day.
Definitely. I'm really looking forward to the live one, and I'll definitely be watching the GSK session. So yeah, thank you both for today. Thank you everyone for joining us and staying right to the end and asking all those questions. Hopefully see you guys on the 27th, or I'll chat with you on Slack, and see you guys on Monday for the next event. So thanks everyone. See you soon.
Thank you. Goodbye.
Bye.